The romantic image of a lone robot in an empty warehouse is obsolete. Modern physical AI deploys fleets of mobile manipulators, human workers on the same aisle, autonomous forklifts, and delivery drones overhead. Cities add curbside robots and passenger vehicles. Multi-agent systems study how many decision-makers coordinate under shared constraints. Human-robot collaboration asks how to share tasks safely when strengths differ. The future is collective, not solitary. Coordination failures look like traffic jams, idle robots, and nervous humans, not algorithm errors on a slide. Collective intelligence appears when coordinated agents solve problems none could alone. A single AMR might stall behind congestion. A fleet reroutes dynamically. Swarms cover large inspection areas faster than one drone. Humans plus robots blend judgment with stamina. The design question shifts from can this robot pick to how does the team maintain throughput when one agent fails, traffic spikes, or a human steps into the workspace unexpectedly. Shared KPIs align local agent decisions with facility-level throughput targets. Coordination requires shared situational awareness. Agents publish pose, intent, and reserved corridors on a common map frame. Time windows prevent two robots from entering the same narrow aisle. Priority rules decide who yields at intersections. Communication may be centralized through a fleet manager or decentralized via local negotiation. When links drop, fallback behaviors must prevent deadlock and collisions instead of freezing the entire operation. Deadlock-breaking rules prevent two polite robots from waiting forever in a narrow choke point. Task allocation assigns pick orders, inspection waypoints, or assembly steps to the right agent. Algorithms weigh distance, battery, skill match, and current load. Hungarian assignment solves small optimal matches. Market-based methods let agents bid for tasks in large fleets. Replanning triggers when delays accumulate or new urgent jobs arrive. Bad allocation looks like idle robots on one side and overloaded aisles on the other while customers wait. SLA-aware assignment prioritizes urgent orders without starving bulk backlog work. Swarm intelligence emerges from local rules without a single commander. Birds flock, robots can too. Separation avoids collision, alignment matches heading, cohesion stays near the group. For drones mapping a roof or microrobots exploring pipes, swarms tolerate agent loss and adapt to obstacles. The trade-off is predictability versus global optimality. Safety-critical warehouses often prefer explicit fleet managers over pure emergent swarms. Communication range limits shape which swarm rules are viable indoors versus outdoors. Centralized fleet managers optimize globally and enforce consistent rules. They struggle when communication latency rises or the manager fails. Decentralized agents negotiate locally and scale naturally, but may produce suboptimal traffic jams. Hybrid architectures use central oversight for mission assignment and local reactive avoidance for safety. The choice depends on facility size, radio reliability, and certification requirements for human proximity. Edge servers sometimes host managers to cut cloud latency for safety stops. Collaborative robots, cobots, work alongside humans without full cages when risk controls are rigorous. Force-limited joints, speed caps, and proximity sensing stop motion on unexpected contact. Hand guiding teaches paths intuitively. Cobots excel at repetitive assist, holding a part while a human fastens or presenting kits at ergonomic height. They are not magic safety devices. Risk assessment, training, and clear zones still govern every deployment. Regular collaborative workflows still need periodic risk reassessment when layouts change. Human-robot collaboration spans a spectrum. Sequential, robot prepares, human finishes. Concurrent, both work on the same assembly with spatial separation. Responsive, robot adapts when human pace changes. Supervisory, human monitors many robots. Effective HRC assigns roles by comparative advantage, robots for heavy repetition, humans for dexterity and exceptions. Interfaces must communicate intent clearly. Lights, gestures, screen prompts, and predictable motion beats surprise. Gesture and gaze cues increasingly supplement screens for lightweight intent communication. Safety standards define performance levels for collaborative operations. Risk assessments map pinch points, reach envelopes, and human walkways. Virtual fences and light curtains add layers beyond software stops. Predictable robot motion helps humans build mental models. Jerky replanning erodes trust. Training teaches workers not to override safeguards. Multi-agent safety compounds the problem. One robot stopping must not blind others to a person entering the aisle. Multi-agent scenarios require visibility of humans to all agents, not just the nearest robot. Fleet management software ingests orders, builds missions, monitors health, and surfaces exceptions to operators. Dashboards show battery, error codes, and map congestion. APIs integrate warehouse management systems, so robot tasks track inventory reality. Version control applies software updates gradually across the fleet. Without a strong ops layer, adding the 10th robot decreases reliability instead of throughput. Simulation-backed dispatch tests policy changes before they hit live traffic. E-commerce warehouses combine goods-to-person AMRs, robotic arms at sortation, and human pickers for exceptions. Coordination minimizes aisle conflicts and empty travel. Dynamic slotting moves fast movers closer overnights. Peak season stress tests allocation algorithms. A human stepping into an aisle should trigger fleet-wide slowdowns, not just one robot stopping, while others continue blindly behind shelves. Slotting and robot missions co-evolve as SKU popularity shifts week to week. Automotive and electronics lines pair fixed robots with mobile AGVs delivering parts. Human stations remain for quality checks and flexible fastening. Multi-agent scheduling aligns AGV arrival with robot idle windows to avoid starvation. And in events pause affected zones without freezing unrelated cells. Digital twins test line changes before moving physical tooling. Coordination errors show up as WIP piles and missed tack time long before robots collide. Changeover windows demand temporary traffic rules so maintenance and AGVs do not collide. Urban sidewalks host delivery robots, cyclists, and strollers. Roads mix autonomous vehicles, transit, and construction detours. Coordination crosses corporate boundaries. No single fleet manager owns the city. Map standards, right-of-way norms, and regulatory reporting become as important as local planners. Physical AI at city scale is a social problem with engineering tools. Predictability, visibility, and fail-safe defaults when agents from different vendors meet. Public incident reporting across vendors helps regulators spot systemic coordination gaps. Agents coordinate through radio, cloud APIs, and on-robot signaling. Vehicle-to-everything shares intent at intersections. MQTT and ROS topics stream fleet state indoors. Humans need signals robots understand and vice versa. Turn indicators on mobile bases, audible alerts, projected paths on floors. Latency and packet loss must be designed for. Silent robots that move unexpectedly destroy collaboration faster than any algorithm bug. Graceful degradation must define safe stops when cloud links fail mid-shift. Labor shortages and rising throughput targets push facilities toward mixed teams of humans and machines. Multi-agent coordination converts more robots into more output instead of more chaos. Safety and trust determine adoption. Workers must feel protected, not replaced without support. Cities need scalable delivery and mobility without gridlock. Investment in coordination software, standards, and training often beats buying another isolated robot that fights traffic in the same aisle. Change management trains supervisors, not only engineers, when fleets go multi-agent. Multi-agent physical AI is how scalable automation actually works. Collective intelligence, task allocation, and swarm patterns organize many machines. Human-robot collaboration adds force-limited cobots, clear roles, and safety discipline in shared spaces. Fleet management ties missions to warehouse and factory reality. Cities extend coordination across vendors and modalities. The lesson is simple. The next leap is not one smarter robot, it is many agents and people moving together without surprise. Invest in ops, standards, and human trust, not just another autonomous unit in isolation.